In the previous chapter, we have seen that if we have a conductor with arbitrary shape, we know that if we put the charge into this conductor, okay, for example, if I put the positive charge into this conductor somehow, we will find that the charge will try to move as far as possible from each other, and the configuration of the charge will be that it will distribute on the surface of the conductor. So it means that inside the conductor, E is 0. And when we, if we know that E is 0, it means that if we look at 2 points, A and B, inside the conductor, and if we want to calculate the electric potential between these 2 points, we have that delta V is equal to the minus of integral from A to B of E dot dr. But E is 0. E is 0. So we have that delta V is 0, right? Or the potential, electric potential will not change inside the conductor. This is very important property of the conductor, that is, we have a constant V inside the conductor. We have the constant V inside the conductor because this is because E is 0. Okay. Now, what is the value of the electric potential inside the conductor? We can answer this question by, for example, if I move the point B to the surface of the conductor, okay, just at the surface, inside, but just at the surface of the conductor, we must have that VA is equal to VB. But point A is inside the conductor, B is at the surface of the conductor. From this, we have that the potential inside the conductor is equal to V at the surface. Okay, you can see that the potential inside the conductor is equal to the potential at the surface. Okay. Next, we also have an important result also, that if I move the point A to the surface of the conductor also, we must have that VA is equal to VB, because both A and B are inside but just at the surface of the conductor. But the position of A here can be any point on the surface. I can put A to any point on the surface. Maybe this point, this point, this point, or this point. And I must have the same conclusion that at every point on the surface, the electric potential are equal. So we have an important result that the surface of a conductor is an equipotential surface. An equipotential surface. Okay. On the surface of any conductor, the electric potential on the surface are equal on every point on the surface and also inside the surface. So we can say that the surface of a conductor is an equipotential surface. Okay. Now, let us see that if we have the situation like this. We have a conductor with arbitrary shape, but in this time, this conductor is hollow. That is, you have the space inside the conductor. Okay. The question is that if you have a hollow conductor like this, or the conductor with a cavity, can we have this conclusion also? Okay. This is quite easy to see, because inside the conductor, okay, if I put charge, for example, if it is I put the positive charge inside like this, again the charge will try to move away from each other. So it means that the configuration of the charge is that they will distribute on the surface of the conductor. Which means that inside the conductor, even there is a hollow inside, the electric field will equal to 0. Okay, the electric field will equal to 0. Okay. Now, if I want to calculate the electric potential inside the conductor, I must have that inside the conductor, delta V is 0, or the electric potential is constant inside the conductor. The question is that what is the situation in the cavity? Okay. To do that, I will choose 2 points. For example, A here and B here in the conductor, but just at the inner surface of the conductor. And I want to I will try to calculate the VB minus VA. Since A and B is inside the conductor, but just at the surface, okay, we must have that VB minus VA is 0. Now, if we use the definition, which is this is the integral from A to B of E dot dr, and this integral can be performed on arbitrary path. So if I choose the path that pass through the hollow, you can see that to do this integration on this path and to get the result to be 0, we must, since the displacement is not 0, of course. So what we must have is that inside the hollow, we also have that E is 0 too. Okay, E is 0 too. Because when we do this integration and it's equal to 0, and if dr, of course, is not 0, which means that E should have 0 value too. Okay, it means that if you have a conductor with a cavity inside, the electric field inside, both in the conductor and in the cavity, will equal to 0. This is very useful. We can use this as a shield, electric shield. It means that if we have a conductor and we make a hollow inside, and if we put anything inside this hollow, in the hollow, it means that we put that thing in the region that has no electric field. Outside the conductor, whatever happens, we will have 0 electric field inside. So we can use this to protect the device that may be very sensitive to the electric field, like the electronic device, okay, by put it into the conductor. What we use now is the conducting polymer. Conducting polymer, which is flexible like a plastic bag, but can conduct the electric, can conduct the charge. I mean, the charge can move freely on this conducting polymer, which is it looks like the plastic bag, but it's like a silver plastic bag, and they always use it as a package for the electronic device. That is because it can shield the outside electric field that maybe can damage the electric device.